Hello and welcome back to our next video on probability. For this topic, we will be looking at the level of significance, or the p-value. And so what I like to think about with the p-value, and that's right down here, is basically what are the chances that we found the results that we did. If the null hypothesis is true, then what is the probability of the observed z-value? And so what we're going to be doing in this particular section is going back to our example up here. Remember, we're running a test that says we got a sample of 185. We're testing whether that sample could have been drawn from a population with a mean of 170. What are the chances that that was drawn from that particular population? And we depend on the sampling distribution of the mean to give us some information about the z-value and ultimately the p-value. So the main thing that you need to know about this is that for every z-value, given the specifics of that particular sample, given n, given the standard error, or sorry, standard deviation, given the standard error of 5, that particular shape of the curve will have z-values that fall at specific numbers. So in this case, a z-value of -2 is equal to 160. A z-value of +2 is equal to 180. And so we're expecting 95% of the time that our sample mean will fall between those two numbers. Now, those two z-values of +2 and -2 can then be converted to p-values. And so those z-values are specific to this particular question, and those p-values that are the corresponding, I'm just going to put convert here, to that particular z-value, those p-values are also specific to this question. So a number of 160 will not always have the same z-value, and also with the number 180. So let's think about the probability for this particular question. We know that 95% of the time the sample mean will fall between 160 and 180 if our null hypothesis is true. And so that's what we're saying down here. If the null hypothesis is true, then what is the probability or the percent of time that the observed z-value will occur? Now, we know about this 95%, so I'm going to try to get you to think about this a little bit intuitively. That z-value, or one that is more extreme. And when we're doing a two-tailed test like we are here, what we mean by more extreme is absolute value of that is more extreme. And so we know that 95% is in here, and then 5% would be either outside, either above or below. And so to have one that's more extreme than 180 is actually a p-value of 0.05. And a p-value, or an x-bar that's less than -2 is also 0.05. The thing that you need to remember about probabilities is that they are all between 0 and 1, because probabilities are positive. And so this p-value of 0.05 just means that it's more than 10 away from 170. So here we have 180 is more than 10 away from 170, and less than 160 is also more than 10 away from 170. So this or one that is more extreme is an important key to that. And for a two-tailed test, that value could fall either above or below. Now let's fill in some of these other probabilities or p-values. A p-value of 0 is actually equal to 1. And so the probability of it being 170, 100% are that value or more extreme away from 170. So when the z-value is equal to plus or minus 1, we end up with a p-value of 0.32. And I'm going to add, let me get rid of this funny little symbol here. I'm going to add plus 3. The p-value that goes with a z-value of plus 3 is 0.027, and plus 4, we're quickly kind of running out of runway over here. It's getting smaller and smaller and smaller and smaller as we get farther away. That value is 0.00007. And so you can see that the chances of having this x bar be this far out, we only have a 2.7% chance of having one that is 185 or more extreme. Now it can happen that we have a p-value, or sorry, that we have a sample mean of 185. It will happen either that extreme or more extreme 2.7% of the time if we're just randomly drawing a sample from this population that has a mean of 170 and a spread of 40. But it's not going to happen very often. And the thing that happened a long time ago in statistics is we decided that a 1 in 20 chance was about right in terms of calling the difference between, well, we think this is pretty likely or we think this is pretty unlikely. And if you do the math, 1 in 20 is equal to 0.05. So somebody just said, okay, well, how about if we have the official cutoff be 0.05? The thing that you need to remember is that that is not just a hard line. The 0.05 is a guideline. In other words, your textbook even talks about between 0.10 to 0.05. That's kind of sort of like the we're wondering if it's statistically significant, but maybe we just happened to draw a sample that wasn't. Anywhere smaller than 0.05, we're pretty confident that that is statistically significant. But again, that could happen about 5% of the time that you get one that extreme or more extreme. Anything that's greater than 0.1, we think, well, you know, the chances of that happening are pretty good. We would expect to see that kind of pretty much all the time. In other words, what we're doing here is we're quantifying the amount of chance that we feel comfortable with when we are taking this sample from the population. So here we have a sample, we drew it from the population. We're hoping to have done this in a random way, such as simple random sample, so that our sample is representative of our population. And so what we're willing to live with is that 5% of the time we end up making the wrong call. In other words, we would reject a null hypothesis that's actually true. So we don't want to do that very often, but we just know that can happen. So that concludes our discussion. Well, you know, I should add a couple of more things. The thing that you'll notice about these p-values is that the smaller and smaller and smaller and smaller they get, the farther and farther and farther away they are from this middle point, this mean. And so that smaller p-value provides evidence against the null hypothesis. So a lot of times people will say the p-value is just less than 0.05 or less than 0.01 or whatever some of those cutoffs used to be in the tables. I think more and more in published research we'll see p-values that are listed as they are actually calculated. So that's kind of an important thing to remember. The other thing that I wanted to mention really quickly about p-values is these were all two-tailed. Everything that we've done up to this point. Now, it's possible to do a one-tailed t-test, and I want to show you what that looks like so that you kind of understand what happens when we do a one-tailed t-test. But in reality, a lot of people feel like it's kind of not as forthright or above board to do a one-tailed t-test kind of like you're almost cheating. You're not, because you tell people that you're doing a one-tailed t-test, but I want to show you what that does to the numbers. A one-tailed t-test, and let me just go ahead and see if I can fit that in here. The z-values are still very similar. The z-value for this middle value is 0, 1, 2, 3, and so on, -1, -2, -3, just like before. However, the cutoff, the 95% of the x's, of the x bars, will actually fall, like let's say we're doing a test that is to the lower, that 95% includes this lower tail. And so what that does is it shifts the 95% p-value over here to the left. And so we end up with a z-value of 1.64 being the corollary. Remember how we convert the z-values to p-values? That's a z-value of 1.64 equals a p-value of 0.05. And so that's going to be down here more around 178 would be our cutoff in order to have a 95% that includes this left tail. So when you do a one-tailed t-test, it's easier to reject the null hypothesis. And so that's why some people feel like it's maybe kind of fudging. Just to get your significance, you moved the line a little bit to the left, or for a right-tailed test, you moved your line a little bit to the right. So for the most part, p-values, we're going to do them as two-sided tests for this course. So that concludes this video. Next, we will move on to running two statistical analyses that are related to this example.